Hi, in the first video of this series, we talked about reaction mechanisms and we talked about multi-step reactions. And we're going to continue on with that today in how to take a reaction mechanism and write a rate law based off of it. So as we learned before that we have many of these chemical reactions, they occur by steps that involve two or more elementary steps. Also, each one of these steps has its own rate constants. Important to notice that some of these steps are fast and some of them are slow. And it's really important to understand the idea that the overall chemical reaction cannot go faster than whatever its slowest step is. Okay, the overall chemical reaction can't go faster than its slowest step. So I'm going to try to give you an analogy here. And it'll be poorly drawn analogy, but it'll be an analogy nonetheless. And let's say we have track and field event going on. And that's supposed to be a track that runners are going to run around. And let's say we're doing a relay, okay? And it's a 4x4 relay. So 4x4 relay, let's say our first runner that steps up for our team, our very first runner that steps up for our team is not very fast at all. This person, when the gun goes off, just barely gets going, and they have to run around this track. And waiting for them behind, are three other runners waiting for that baton, and every one of these runners is blazing fast, super, super fast. They're just waiting. Come on, give me that baton. Give me that baton, because we can run this race. But that first runner is just slowly making their way around the track. So the problem with this is that first runner is determining how fast they can finish the 4x4 relay. They're keeping them from winning by going slowly, right? So chemical reactions are kind of like this sometimes. So if we have multiple steps, what can happen is one of the steps can keep all the other steps from going quickly because it determines how fast. And we call this slow step, we call it the rate determining step, the rate determining step. And we're going to talk about how we can use the rate determining step to write our rate law off of the rate determining step, which is typically the slow step. So let's get into how do we do this and how do we incorporate in what we learned in our last video on mechanisms. So here's our example. These are going to be mechanisms that have an initial slow step, much like the analogy that I gave you of the relay. We're going to have a slow runner at the beginning. We're also going to have a slow step at the beginning. So first thing we're going to do is we're going to write the overall reaction for these two steps, a proposed overall reaction. So here's what we see. We see that nitrogen dioxide is going to collide with nitrogen dioxide. It's going to be bimolecular to form nitrogen trioxide and nitrogen monoxide. Okay, and it tells us this is a slow step, meaning it is going to go at its own leisurely pace. Then what is happening in our fast step is we have nitrogen trioxide. The same nitrogen trioxide that was produced in our slow step in step one is being consumed in step two. And we remember any time that's produced in the first step and consumed in the second step is also called an intermediate. Now, so this intermediate, this nitrogen trioxide, is needed to get the second reaction going. And then we're also going to use up some carbon monoxide to produce our products. Now, this second step is happening fast. As soon as the nitrogen trioxide is produced, it's consumed immediately. Just waiting for it. Just come on, make some more nitrogen trioxide so we can use it up and keep this reaction going. Okay, so that's just really what's happening in the reaction. But before we talk more about that, let's write the overall reaction. So remember, on overall reactions, if we have something that is present on either side of the arrows, we can cancel it out. So for example, this nitrogen trioxide and nitrogen trioxide could cancel. This nitrogen dioxide here and nitrogen dioxide here is going to cancel. And we can write our overall reaction as, NO2 plus CO yields NO plus CO2. And so that's going to be our overall reaction right there. Now we're going to write a rate law. Now, rate laws off of initial slow steps are relatively easy to write, because all we have to do is identify the slow step. And so there's the slow step. And remember, when writing rate laws, we always write rate is equal to K. Now, and we're going to only include our reactants. So in this case, our reactants are the nitrogen dioxide and the nitrogen dioxide. Now we have two of them, so what we're going to do is just write NO2 second order, and we write second order because there were two of them. It's a bimolecular, just like that. And there we go. We just wrote our rate law. It's a second order rate law based on NO2. We can't write it. We don't write it on the fast one if we have an initial slow step. Again, that slow step is our rate determining step. In our next video, we'll talk about what happens when you have an initial fast step.